My name is Johnathan Woodside. I'm a senior mechanical engineer with Gresham Smith, and yes, we do engineering and commissioning too. That's been a really interesting question to answer the last couple of days. This is Stephen Metzgar. He's a senior commissioning authority with Gresham Smith, and we're going to talk today about 10 of the most common commissioning mistakes that we see while doing commissioning, and perhaps even have made once or twice. Well, we can all probably agree on this definition of commissioning because we've talked about it a lot the last day or so. We live it, we know it. Those of us who are practitioners, those of us who have been parts of commissioning teams. But within the last couple of years, the word commissioning has become a lot like the word sustainability, in that everybody kind of thinks it means something a little different. So we always like to start off to make sure that we're all on the same page with what commissioning is and is not. But commissioning is essentially the process of coordinating design activities, construction activities. We are the glue, as Al puts it, of holding the team together. So we are essentially a third party that's overseeing the process of design and construction and ensuring that at the end of the day, when the design is handed over, that it functions and operates in accordance with those design documents and the owner's project requirements. So the process of commissioning, of course, looks like this. It's broken up as the ACG and ASHRAE tell us. We've got the 5 different phases. There are obviously pieces and parts and steps in each one of those phases that have to happen that lead to the next. We know that this is what a comprehensive commissioning process looks like, and in order to walk away from a project and say that it has been commissioned, these things we would like for them to all have been completed, boxes checked, commissioning reports, systems manuals, all those things completed and signed at the end of the day. That being said, we're going to talk about some of the common mistakes that we have seen on a number of different projects, but for the sake of the discussion today, we're going to talk about one project that we're really kind of using as a case study to talk about all 10 of those mistakes that we saw happen at one time. The project is a dental clinic project that we worked on in Aurora, Colorado for the Corps of Engineers. It was on Buckley Air Force Base. We were, as a design firm, we were actually an AE3, so if you guys are familiar with government work, we were essentially just an off-team reviewer specifically for the electrical component. So AE3, architect and engineer, third-party reviewer. Basically, the project had its own design team, the project had its own commissioning agent, and we were essentially just reviewing electrical drawings for conformity to UFCs and things like that. Couple of interesting things. The reason why I mention that is because all of those things sort of play into the chain of events that kind of led to where we got to and some of the mistakes that occurred. The project was phased in 2 different phases, and this particular Corps office has a rule that if a project is under a certain dollar figure, that you don't have to commission it, which makes a lot of sense. So there was a project, the first phase of the project was over this threshold, which means that it was commissioned. So the project consisted of 2 air-cooled chillers, it consisted of a couple of condensing boilers, pumps, accessories, so forth and so on. So what ended up happening is the first phase included an air-cooled chiller, and it included a condensing boiler and the pumps that was commissioned. The second phase was sort of pseudo-commissioned. It was really not commissioned. It was just a checkbox by the engineer. So it was not, that part of the project was not commissioned. So that second part of the project, once everything was online, once all the chillers were operating, the pumps, that part was not commissioned. So I say all that to say this. We're going to talk a little bit about where some of those mistakes occurred. The way that we became involved in the commissioning process after the fact was we got a phone call from our client, and they said, can you guys come and take a look at the chilled water system because the chiller keeps tripping on low flow. And they were in the process, the contractor was in the process of demobilizing, turning the building over, getting out of town. They had a couple of weeks to get all that finished, and they were having problems with the chilled water system not working correctly, and the chillers, in fact, were tripping on low flow. So the first phone call that we got was, can you guys come out and take a look and tell us what's wrong with the chilled water system? So Stephen's going to talk for a few minutes about some of the things that we found, some of the mistakes that we see regularly with chilled water systems, and in particular at Buckley Air Force Base.
So the first thing they wanted us to do Am I on? Can y'all hear me okay? Do what? All right, so the first thing they wanted us to do is to review the design documents. So, hey, can you make sure that the design engineer designed the chill water system correctly? And a lot of people, for some reason, a lot of owners think that the larger the chill water plant is, the more it needs to be commissioned. And the smaller chill water plants do not need to be commissioned. And I argue that usually it's the smaller air-cooled chillers and the chill water systems that need to be commissioned probably more than the larger typical water-cooled centrifugal chillers, just because the larger the chill water plant, the larger you can hide your mistakes, whether it's controls that are making mistakes or whether it was the design engineer that made the mistakes or whatever the mistakes may be, you can still hide a lot of those mistakes because you have a lot more mass, a lot more volume, and a lot of times little mistakes don't hurt you as bad. So the first thing I wanted to look at was, it was an 80-ton chiller. First thing I wanted to look at was, do I have enough volume in the water or enough volume in the system so the chiller doesn't short cycle? So I wanted to make sure the buffer tank was sized correctly. I also wanted to see if the minimum flow bypass was sized correctly. A lot of engineers, for some reason, will size the minimum flow bypass for line size bypass and not size it for minimum flow across the chiller. And that causes a lot of control issues when you get down in low flow issues. Especially with this system, you only had 3 air handling units. So if one chill water valve fluctuated quite a bit, it affected the flow quite a bit. So all that kind of cascaded and made things worse. So once we verified all that and realized everything was good, we went out to the site. So when we got out to the site, the first thing I wanted to do was I wanted to check the chill water flow and make sure that the differential pressure was working correctly, and to make sure the pumps were operating to maintain this flow. So when we get out there, one of the things that, it's hard for me to see this screen, I might step down. The one thing that we did was we asked the control contractor, what is the set point that the test and balance needed to make sure you got adequate flow through all your chill water coils? First thing they said is, we don't know. We haven't seen the test and balance report. I'm like, you have not seen the test and balance report? They said, no. I said, okay. So they had it set at 30 PSI because they kept having low flow issues across the chiller. So first thing they thought is, well, we'll just increase the DP, ramp the pumps up, and get more flow. I said, okay. So we had to call the test and balance firm to figure out what the differential pressure was supposed to be. It was actually supposed to be set at 15 PSI. So we had to lower the DP to get it back down to what the design or what it needed to meet all the chill water flows. So that brought us to our next slide.
And since we wanted to go the extra mile, we were actually able to set the DP lower than that. We ended up setting it at like 11.5 or 12.
Yeah, 11.5 or 12.
Anyway.
So
toot our own horn a little bit, but
I just want to make sure everyone, I come into a lot of these presentations. I just want to make sure everyone gets stuff out of the presentation, make sure it's an educational presentation. So the first thing we did was verify that it was designed correctly and had enough volume of flow so you didn't short cycle the chiller, and the bypass valve the bypass line was sized correctly. Second thing is, when we got on site, the other mistake that is commonly made is not verifying differential pressure with the test and balance. There's no communication between the two. So now we move on to the other mistake, which was the chill water flow bypass valve operation. And correct me if I miss anything.
If you guys have we don't want to wait. We're super informal. We all do this, right? So if you guys have questions in the meantime, please don't wait till the end. Please ask us now. So as we're going, please stop us, raise your hand, ask questions. We'd like to talk about it as we go.
And a lot of y'all probably have more experience than we do, and if y'all have a question or want to know why we arrived at the stuff that we did, then just let us know or ask the question. So when we got out there, of course they had the DP set at 30. We're like, man. So they had the bypass valve actually controlling to the system differential pressure instead of the differential pressure across the chiller. So everyone knows in variable primary, the main purpose of a bypass valve, the sole purpose for living, is to maintain minimum flow through a chiller. It has no other purpose of living except to maintain minimum flow. It doesn't care about anything else in the system. So they actually had it controlling to the differential pressure in the system, which was set for 30. Not only that, is they had the bypass valve operating backwards. So as pressure increased, it would close. As pressure decreased, it would open. So we were like, man, that's jacked up. So then we got to the point of, all right, so what is the real issue after we found all this? So what we found was the control contractor decided to for some reason, take the differential pressure sensor out of the loop. Just took it out. So there was nothing reading differential pressure across the actual chiller barrel, which that's the sole purpose of the minimum bypass valve, was to maintain minimum flow. So they didn't have any reason or any verification of reading what the flow was across the chiller. So my personal preference for people who do design, if there is, this is probably filled with commissioning agents, but I would rather have a flow meter that you can actually read the flow to operate your minimum flow bypass valve instead of reading a DP, because a small amount of differential pressure increase or decrease is substantial when you're reading DP versus actual flow. So they didn't have, for some reason they took the differential pressure sensor out, so they weren't reading that. So we were out there supposed to just document what we have found, but we realized what we have found, it would never work. So after we have left, they would still have all these issues. So we just took it upon ourselves to go ahead, which was probably a mistake if you're looking at it from a risk management type view, but we just went ahead and fixed it. So what they did is they had differential pressure sensors, or they had pressure sensors in the inlet and outlet of each chiller. It's not ideal, but we had to work with what we had. So we just calculated the pressure difference. We took the inlet pressure, outlet pressure, subtracted it, and said, okay, there's where we are. We had, I think the minimum flow requirement was, 3 psi or something, 2 psi. So we just made it 3.5 because it's probably not extremely accurate. So for one, I don't know why the control contractor took the differential pressure sensor out, but two, I don't know why the commissioning firm or the commissioning agent didn't pick it up. I don't know why the design engineer didn't pick it up. So there's several mistakes there, and I don't know. There's just several mistakes that the commissioning agent made. So that's just part of it. So we were able, and another thing too on chill water systems, when you're testing, me personally, and I've kind of learned this working at my previous firm, when you're testing minimum flow bypass to ensure that all minimum, to make sure that it will not trip the chiller, I personally try to shut as many chill water valves as possible, if not all the chill water valves, and then open up my bypass valve, and then lower my VFD down to where I reach that minimum flow threshold. And then that way I know that regardless of what the load is in the system and how low the load goes, or for some reason all the chill water valves close and my chiller is still operating, I still maintain minimum flow through that chiller. Small systems are a little bit worse than larger systems because you'll probably never reach that threshold of your minimum flow speed on your pump. But a lot of people say, arbitrarily put out 15% on your VFD and away you go. Well, in small systems, that minimum, as your DP drops, that minimum flow might be less than your actual minimum flow across your chiller. So I like to verify that I'm going to maintain minimum flow across that chiller at all times. So that's the main purpose. Just make sure the chiller doesn't trip. So anyway, those are the things that we found on the chill water side. So any questions? And I don't know, y'all might see that all the time, go out there, but it's just stuff that we have found that I don't know why the commissioning agent did not look at some of this stuff and figure out, hey, this isn't going to work.
So the first phone call we got was about the chill water system. While we were there, they said, well, we're kind of having some problems with the heating water system too, but it hasn't really, it hasn't run enough yet for us to really know what's going on. So just look at this, and then if it continues, then we'll call you back. So again, this piecemeal approach to troubleshooting, and as Stephen mentioned, one of the things that was a little bit of a challenge with this project in particular, number one, was just the timing of when we were involved in actually doing this. But secondly, were the number of stakeholders and what their goals were. So, we were engaged by our contact who held our contract through the contractor, through the USACE. So you had the Corps of Engineers, you had the building owner, you had our client, and they all wanted different things. The guy at the building just wanted the chiller to run, right? So the engineer at the building just wanted his new building to work and wanted to stop getting phone calls. Our client and the Corps wanted us to just document all this information in a report and hand it off, and then they could determine liability and figure out how to fix it. Which Stephen's comment earlier about, ideally, this should have been documented in issues log, should have been handed off, somebody should have fixed it, but we couldn't walk away from the building owner and leave something that didn't work, because that's what we were there for. So obviously,
we wrote it up in our report.
Yeah,
we just noted what was wrong, but we actually
everything was documented. I'm not saying that, but everything was documented. But it was important for us in just navigating all of those politics to make sure that we handed our client a building that worked. And since it was something that we knew how to take care of and how to fix, we did so. Second phone call was about the heating water system. Similar situation. This conversation was, well, our condensing boilers are tripping on high limit or low flow. And essentially what was happening after we did a little bit more investigation from that initial conversation was the heating water system, the boilers were cascading, they were in a master-slave arrangement. So under normal conditions, you'd have one boiler run, and in order to equalize the runtime, they were switching at 2 a.m. What was happening at 2 a.m. is the boilers would switch, the second boiler would trip, and they would never rotate back. So they would essentially both just trip on high limit, low flow. And so this same building engineer was having to go out at 3 a.m. and reset the boilers, and he was not happy.
One thing that we found, do y'all deal with a lot of Lochinvar night boilers, condensing boilers?
Lochinvar rep isn't in here, is he?
Yeah.
Or she?
So what we have found is they rotate their boilers at 2 a.m. in the morning, and that is something you cannot change. It's something that if you say, hey, I want it to equalize runtime, well, they equalize runtime by 24 hours, and they decide 2 a.m. is the best time to do it.
We could change it to PM. We could make it 2 a.m. or 2 p.m.,
yes.
But you couldn't change the time. You couldn't change the
time,
2.
But you could fake it out to read 2 a.m. or 2 p.m.
So it's either going to be during normal operation or at nighttime. So obviously, ideally, his goal was, well, I just want them to switch at night when nobody's there. They switch, rock and roll, everything's fine.
And there is a huge distinction between the manufacturer rep knowledge versus the actual Lochinvar out of Lebanon, Tennessee knowledge. So we'll get to that in a minute.
So the challenge was, we're having these boilers are tripping on low flow. We narrowed it down to, okay, it's only happening when they're switching. They're only tripping on high limit, low flow whenever they're switching. That's the only time that it's happening. Under normal operation, when the boiler's running, when it's ramping up and down due to load, everything is fine. So the first thing we did was we took a look at the drawings before arriving, and then we got a set of updated drawings when we got there, which were different. But the most obvious thing that we saw was there was not adequate minimum flow for the boiler. So variable primary on the heating water side, there was not a bypass for the heating water, and there was only one three-way valve in the entire system. One three-way valve on one unit. So I think the minimum flow on that boiler, I think they were like 600 MBH. I think the minimum flow was like 20 or 25 GPM or something like that, and there was one three-way valve for like 3 GPM. So there was not enough minimum flow in the system to maintain through the boiler. So that was number 1 or number 4 on the list of 10.
So when you're doing design reviews on a condensing boiler, just make sure, a lot of people, Lochinvar recommends doing a pump at the boiler, but design engineers can do a variable primary for condensing boilers. Just make sure there's a bypass somewhere. I think Lochinvar likes it to be out in the system, out at the reheat coils and stuff. Just make sure that amount of bypass will total the minimum flow of the boiler when you're doing your design reviews.
Yes, I mean, depending on how large the system is, obviously we're used to seeing three-way valves out in the system so that you can maintain heating water flow for demand and all that kind of stuff. But there wasn't enough in the system to maintain flow, so we knew that we had a flow problem in terms of being able to get it when it was under minimum load conditions. The second thing with the heating water system, or number 5, is the master-slave control. And so the way that this arrangement was set up, and we're going to get into some control-related things here in just a few minutes, but the way that this master-slave arrangement was set up was that there were only one set of sensors in the system. So the master boiler had a flow measuring device, it was measuring temperature, it had its own set of sensors so that it could operate by itself. And the idea was that, according to Lochinvar, was that, well, as long as that boiler has power, then the slave boiler is still able to read through it and read those sensors through the BAS.
It's a pretty common practice. I'm sure everyone in here is.
But the problem is when the master boiler loses power, that all goes away. So yeah. The slave boiler couldn't see those sensors if the second boiler lost power. Now, obviously, nobody failed the boiler except us, because we said, hey, what if we decide to turn the power off? Then what happens? Well, we saw that we lost control of that slave boiler, so that was another issue. That was not necessarily contributing, but we found that, obviously, if they were trying to service one of the boilers, and if they were trying to service the master boiler and turned it off, which was one of the conversations we had with the building engineer, then everything goes away. That boiler can't maintain control. Obviously, unless you put it in hand and all that kind of stuff, but that's not a great idea.
Well, the remedy of that, Lochinvar told us to fix the master-slave issue. If you're going to do a master-slave setup, which is pretty common to get the efficiency out of those condensing boilers, is they want you to do master-slave. So when one ramps up to a certain point, the other one will come on and ramp up, and they can run at a lower percentage and stuff to get your efficiency. They said if you have a master-slave setup, then each boiler, if you want to fail the master boiler, each boiler has to have its own set of sensors. So if I have 2 boilers, then that boiler needs to have its own supply temp, hot water supply temp, everything that the master boiler has. So, and you can even set it up in the program, so if you fail that master boiler, it'll just switch over to the slave and it'll come up and operate as a standalone boiler. So that might be something that y'all are interested in, because that's one of the things that maintenance guys always say is, well, this master-slave setup is great until I turn off the master boiler, and then what happens? Well, you're out of luck. You don't have any hot water. So that was the remedy that we put in our report to fix the master-slave issue if you ever lose power at your master boiler. So, and the commissioning agent for some reason did not catch that there was no disconnect at that boiler, at the master boiler. So we had to go.
Yeah, we're running to the panel. Running to the panel, turn off.
Yeah, circuit. So just another thing. It was just a combination of a lot of bad stuff. Anyway, go ahead. Sorry.
All right. So in terms of what was happening when those boilers were transitioning over at 2 a.m., the first part of that was the isolation valve operation. And isolation valves on chillers, on boilers, are always, a lot of times can be problems. Number one, if there's not one, that's a problem. In this case, there was one, but the problem that we found was that the stroke time was 10 minutes. So what happened, I think there was an S on the schedule and somebody thought it was an M, and it's consonant's a consonant.
And by the way, this was set up by the manufacturer rep. So.
Yeah, the Lochinvar rep came out and started these up. So we talked, while we were troubleshooting the boilers, we had the local Lochinvar, or the Lochinvar person that supposedly started these up. We talked to them, and then we also talked to the guy from the
main office,
the Lebanon, Tennessee, which is where Lochinvar, these boilers are made. We had him on the phone, and it was Yeah, though they need to talk to one another, just to be quite honest. But anyway, so they started this boiler up. So what was happening is when these boilers were switching over, under whatever flow condition, instead of flowing all that water through the boiler that was being switched over, so we were switching from master to slave, hot water goes through the slave boiler, it was just splitting the flow. So you were splitting the flow. The leaving water temperature was too high, the flow was too low, so you were tripping on low flow, high limit. So obviously the quick fix there, and what we did while we were there was to just change the valve stroke time. So we had the controls contractor with us. We were able to fix that fairly easily. But you know, such a simple thing that should have been taken care of, like Stephen said, should have been addressed by the manufacturer rep and then verified later on during FPTs was not.
Well, and also, I guess to go back to the chill water system, if you have a chill water plant that has a setup like this where you can operate multiple chillers, I've seen that the isolation valves, when you're switching over, even staging up and staging down, probably the isolation valve stroke time on those chillers is the majority of your problem, because you reduce the flow by half, you increase your delta T, next thing you know you're out on a chiller because you're. But anyway, that's just when you're doing large chiller plants or even small chiller plants, just make sure that the stroke time and your isolation valves are correct so you don't get into those nuisance trips. Sometimes valves are adjustable, sometimes you have to order another valve. So anyway.
And then the final thing on the heating water side, which is number 7 of our total 10 here, is the firing rate schedule. The way that what we learned here, and this is really kind of a PSA for just package controls. So ERVs, boilers, whatever, anything that has package controls, a lot of times as commissioning agents, as engineers, as designers, engineers especially don't always think about what package controls can and can't do, right? So you've got a sequence of operation that's measuring, airflow and fan speed and all these different things that the packaged controls maybe can't do or can't provide an output for, or they're just unable to do that.
And engineers love to show everyone how smart they are, so they complicate the sequences way too much. So,
yeah, so
they're smart people.
Easy.
Sorry.
There might be some engineers on it. Sheesh. I don't know if I can go on now.
That's okay. Go ahead.
Yeah, I mean, absolutely. So the first part of this whole conversation is we need to understand, when we're, obviously as engineers, we need to know what the capabilities of the equipment are. Not just, like I said, not just for boilers, but anything with packaged equipment. And, and as we said earlier, our reps need to know that too, and the manufacturers. But if we don't understand what the controls are capable of controlling and measuring and doing, then obviously that's a problem when we're out trying to start things up, trying to test things. So as it pertains to those package controls for the boiler, the firing ramp schedule, the thing that we learned here, the main 2 things that were causing this high limit, low flow situation, or the boiler to trip on high limit, was the isolation valve operation and the firing ramp schedule, or the firing rate ramping schedule. So what was happening is that slave boiler was set up to fire at like 50, it was set to go to 50%. That was its first step. So it went to 50% for like 10 minutes, and then it went up and up and up. So what was happening is when that isolation valve was closing so slow on the master boiler, you had a low flow going through the slave boiler. You had the slave boiler firing up, it was going to a high fire rate. So, obviously the water temperature leaving there was much higher than it needed to be, so it was tripping. So we had to go inside, we had to navigate our way through that little tiny screen of, control and try to figure out how to change the firing ramp schedule. Once we found it, a few phone calls later of talking to the Lochinvar rep and how to get in there and what, there were a few. The other thing about package controls is, everybody's kind of they've got their own naming convention for things. So they have these proprietary names for what certain things are. So we were trying to figure out how to make this thing control just based on the leaving water temperature, and Lochinvar had some kind of weird name for it. So we're like, oh, is that what this thing is? Yeah, okay. So that's what we want. We're not trying to establish some kind of stepped configuration. We want it to control based on leaving water temp. So at any rate, adjusting the firing ramp schedule and the isolation valve were the two things that ultimately got us for the boilers to be able to rotate like they were supposed to and not trip on a high limit situation.
Go ahead.
Do you want to talk about the controls?
Yeah. And this is
board?
another thing. You talk about factory authorized startup. They jumped out the flow switch for some reason. So you didn't have flow. He was saying it tripped on flow, but it actually tripped on hot water.
Yeah.
High limit, high temperature limit. So they jumped that out. Also, the control contractor was supposed to have an alarm contact. So anytime the boiler failed, they would know it. You see up there in the top left where it says alarm contacts. I don't know how the BAS is reading that, you know. Runtime contacts are supposed to monitor runtime for the boilers. There's a point there for you to actually monitor runtime. So I don't know, even if this was a standalone boiler and they didn't go to the next phase, why didn't they, and I don't know why Lochinvar does this, but the flow switch is something that you do in the field. So it's not something that they do at the factory. But
Are you saying that the BAS submittal did not show that wiring to be done?
no, it showed it to be done.
Yeah.
Oh, okay.
Yeah, it was actually in the submittal, in the control sequence,
Okay,
in the
so it's the startup guy and BAS guy both,
Yep.
felling.
abrogating their responsibilities
Right.
in that regard, and the commissioning agent missed it also.
Yes.
Yeah, it was a
Over 3.
complete and
0 for
utter.
3.
Yeah.
So when you get a board, when Lochinvar ships a board out, they'll have jumpers on the flow switch, they'll have jumpers on the gas pressure, they'll have jumpers on the louver switch. They'll have jumpers that come from the factory like that. And it's the manufacturer startup guy that is supposed to tie all this stuff in. So when you get a board like that from the factory, all that stuff is already jumped out. So it's just a mistake on their part. So and they could, by having runtime and stuff, the control contractor can switch the boilers anytime they want. You know, that's not. They had the option of being fully controlled by the control contractor. So, but these are just some of the stuff. I just wanted to. Are we just about done? Are we running out of time?
No, you're good.
Okay. But I just wanted to, the biggest thing is just the common mistakes that we see. And I know y'all see the same things. Y'all are very experienced, y'all. But it's just something that, for some reason, I think I was talking to someone that came by our booth. He called them office commissioning agents. I called them drive-by commissioning agents. You know, you just drive by the building, you're like, there it is. Or they just say, well, we got all the documents, we're going to check all the boxes, and I'm not going to leave the office, and we're good. So I don't know what kind of commissioning firm was out there, but this is what you get into sometimes.
Last but not least is a design build. This is just a misconception that leads to mistake. Is a design build requires less attention, not more attention. Design build is really perceived as the engineer is working directly with the contractor, and they've got all these details sorted out. They've got controls figured out. They've got all these coordination things worked out. But in reality, my experience with design build has been the contractor's brought on board essentially just a price, right? We're designing and we're sort of handing documents over, and the contractor's saying, yep, that's close enough, that's good to go, that's what I priced, or I need you to change manufacturers or whatever. So as a result of that, a lot of times the commissioning agent, I think, in this case, was kind of lulled into this false sense of security, knowing, well, they've already sorted a lot of this stuff out, so I don't need to spend as much time on the design review because these guys have already coordinated all this stuff. Or I don't need to spend as much time picking around the mechanical room because I don't need to, I know the mechanical contractor installed it exactly as the design drawings have it, those sorts of things. So making sure that we're being attentive regardless of whether it's design build, design bid build, can lead to some pretty serious errors, as we've seen, not just on the commissioning agent, but really just across on the entire team. Just making sure that we're being attentive and observing those things. Wrapping up, overall picture, obviously we know this, we do this. You guys, everybody in this room, when I say we, we get it, that that commissioning is a comprehensive process. It's not a piecemeal approach, and that's, we see it so often, especially when we look at this process. We have owners and clients that say, well, man, that's expensive. Can I, we had a client recently say, well, which things can I pick off here that are like of the most value? I don't really want to pay for all of it. Can I pay for 50% of it and still get, 90% of the benefit? I get where they're coming from, but it's such a challenge to just cut things off or cut things out. And as a result, you see just this project example that we've been talking about. When you get started late, you're not conducting you're not in the pre-design phase, you're not conducting a real design review, you only do half of the project, perhaps you only commission certain systems, those sorts of things. It's so important to approach commissioning in the most comprehensive way that we can based on the resources that we have. So thank you for your time.